Good morning, class, and this session is being recorded. We are looking at section 2.4, limits, algebraic method. Again, if there is a privacy issue, please make sure your audio video is muted and all the time. The chat, don't put anything in the chat. You can even change your name to your initials. We looked at sections limits of sequences, limits of functions at infinity, limits of functions at finite numbers, and we're going to finish the chapter by looking at algebraic methods. So here's the synopsis of what we've covered. Let's so quickly recap. We looked at the definition of a sequence, which is a list of numbers, and then convergence and divergence, which simply put means, let me just grab my laser pointer. So basically, let me get rid of this floating thing. Okay. If the limit exists when you take a limit of a sub n when n approaches infinity and you can pinpoint that into L, you say it's convergent. So it converges to L. But if it's infinity or negative infinity, or if it doesn't exist, it diverges. Okay. And as I mentioned, just basically we plug in and observe. There are others that we want to discuss here. For example, in this case, basically this theorem says when the denominator is huge, the limit results in 0. If you're raising a number to the power as n goes to infinity, depends on the base. If the base is between not only 0 and 1, it's between -1 and 1 goes to 0. And if it's larger than that, then 1, it goes to infinity. Then the geometric sequence and their sum, which is a geometric sequence, a series, we have the formula. If r is between -1 and 1, it simplifies to a over 1 minus r, okay? So having said that, this is also the geometric sequence and in recursive format and explicit format. If we add a constant, an example of that would be giving medication to patients. We have the following solution. B sub n is B sub 0 or A, B sub 0 or A depending on the text, r to the power of n plus the constant times 1 minus r to the power of n over 1 minus r. And of course, we discussed the horizontal asymptote and what it means. And basically, when you take a limit and you let the function, the limit to, it converges and the limit does exist when x goes to infinity or negative infinity, then y equals L is the equation of what we call a horizontal asymptote, Okay. Then we looked at more stuff. Okay, so let's quickly recap. The definition of a limit of f of x as x approaches a equals L, meaning when x gets closer and closer to a, what happens to the y coordinate? That's the idea behind the limits. As far as the vertical asymptotes, if x approaches a or a from any side, and the limit blows up to infinity or negative infinity, it gives rise to the equation of a vertical asymptote x equals. A limit only exists if the one-sided limits are identical. That means the limit of f of x when x approaches a from the left is the same as the limit of f of x as x approaches a from the right. Finally, as far as all these graphs, all of them, the limit as x approaches a is the same, which is L. Okay, all of them from the left and right of a, we hit for this point having the y coordinate equals to L. But the difference is this one, f of a is also L. There's no hole, right? This one, there's a hole. And since we have a solid point, f of a is the y coordinate of this green point, which is B. And this one, it's not given, it's undefined. Yet, in all cases, the limit exists and the limit is L. And that's very interesting. So that has got to do with understanding the concept of a graph. And I can't emphasize this enough, class. So let's look at this limit laws. We are not going to use it often. Ultimately, we plug in, but we should be familiar with that. If the limit of f of x exists, the limit of g of x exists, and we have a constant, basically we can separate them. If we have a sum And we are taking a limit of a sum is the sum of the limits. The limit of the difference is the difference of the limits. If you have a constant multiple, take it out. If you're multiplying them, do them individually. If you're dividing them, do them individually. The denominator can't be 0. However, we normally do direct substitution. So by definition, the limit of f of x as x approaches a is equal to f of a. That means if the limit is equal to the functional value, the function is continuous at that point. Every function that we have studied, functions with the direct substitution property, are called continuous at a. Every function that we have studied is continuous in their domain. So we need to be familiar with the functions and we need to know their domains. Okay. Now, for example, polynomial functions, their domain is all real numbers. Okay, class. I hope everybody remembers some stuff from algebra, of course, but we come across it. I'm going to mention it again. However, it's important to know. Now, this is an example that I'm going to go over the limit laws. Just at least you have seen it and you've been exposed to it, okay? But as I mentioned, we will basically plug it. So let's observe. According to the limit laws, we have to cut them into pieces. So let's do that. So we cut this into 3 pieces. Now we want to take a limit of each piece. In order to do that, you can only replace the x when it gets to limit of x. So this is the same as the limit of x as x approaches 4 to the second power. The second one, -3 sits in front. It's a constant multiple. Now replace it with 4. So this becomes 4 squared, which is 16, minus 3 times 4, minus 12, plus, that's a constant, so itself, which is 7, and it gives us 11. However, as I have mentioned before, if you just plug it in the first place and observe, that works out. I wanted you to be exposed to limit laws or limit properties. However, when we plug in, what happens? And that's, I want to remind you what we have mentioned. So plug in and observe. If you get to some number, any number, you're done. If you get 0 over some number, when we say some number, anything other than 0. So 0 over any number other than 0. We are done. If you have a number, any number other than 0, over 0, when you divide any number by 0, ultimately it goes to infinity. However, you need to figure out its positive or negative infinity, and we have seen that before, and the methodology was basically literally you plug in a number nearby and you observe whether it becomes 0 from the left or right, because 0 is the only number class that from the left and right, it has different signs. Any other number, if it's a positive number, both sides are positive. If it's a negative number, both sides are negative. However, most of the time, we do a case that, or cases, I should say, known as indeterminate form. Indeterminate forms. Some of them are as follows: 0 over 0, infinity over infinity, infinity minus infinity, so on and so forth, okay? And so what happens, that basically means we have to work at it. We need to use our algebraic techniques to figure it out. Okay, let's look at the next example, and I'm going to turn off the video in case, because sometimes your screen gets blurry. And by the way, please let me know if it does by any chance. That means there's an internet connection problem. We are evaluating the following limits. And again, in essence, we are going to use the limit laws. And to do that, we have to stick with individual limits first. So here's what's going to happen, class. We are interested in finding this. So let's look at the limit of f of x as x approaches -2, and then g of x as x approaches -2. Then we deal with this. So as you can see, f of x is the red one, and g of x is the blue one. So class, again, you don't have to participate. I'm just asking a question. If anybody want to answer, you're more than welcome to do that. Let's find the limit of f of x as x approaches -2. Can anybody tell us what the answer is? This is number -2 from the left side and the right side of that. That's what we are going to approach. From the left side, okay, we are moving towards this hole, okay, which has y coordinate 1. From the right side of 2, we are moving towards the same hole, having the same y coordinate. Therefore, we say the limit of f of x as x approaches 1, as x approaches -2 is given, and that is 1. So that's very straightforward, class, okay? I hope everybody's comfortable with that. Let's look at the next one, which is g of x. We are going to look at the blue one, okay? So -2, the left side of -2 takes us here. The right side of -2 takes us to the same spot, okay? And this has a y coordinate what? -1, -1. So basically, you are going to separate the limits as this piece plus 5 times this piece. So the first piece, you plug it in, so you get 1 plus 5. The second piece, -1. So 1 plus 5 times -1, they add up to -4. Very straightforward. Okay, everybody? Very straightforward. Let's go to the second part. And to do the second part, you need to find, again, the limit individually. Okay. So let's just discuss the f of x. Okay. As x approaches 1. So here's number 1 from the left and from the right. The left takes us here. The right takes us to the same spot. So I hope you see that the limit of f of x as x approaches 1 from the left and right has the same value, namely 2. However, okay, this limit doesn't exist because limit of f of x as x approaches 1 is 2, but the limit of g of x as x approaches 1 doesn't exist. So I'm asking you, why is that the case? So can anybody tell me why this is the case? I showed you the limit of f of x as x approaches.
Is it because they don't equal each other because they're not the same
Perfect.
from the left hand? Yeah.
Perfect. Perfect. So take a look. If you are looking at the g function, is the blue function, okay? And so when You're looking at x approaching 1. Here's number 1. From the left, you're in this branch, you're moving towards this hole, and that gives you the y coordinate, which is -2. On the other hand, from the right side of number 1, you're in this branch, bringing you to this point, which has a different y coordinate, namely -1. So because this limit doesn't exist, because the two are not equal, that's the reason. Therefore, the limit of the product doesn't exist. Okay, class? Therefore, the limit of the product doesn't exist. And I can't emphasize this enough. Okay. Now, of course, you could have a different approach. You could actually evaluate the limit. You can actually evaluate the limit. So I'm going to show you the limit, and I highly recommend you guys try this on your own, making sure you can come up with that. The limit of f of x, g of x, this as x approaches 1 from the left, and I have actually the details. You just multiply and you get -4, but on the right side you get -2. Although you don't have to go this far, everybody. You don't have to go this far. I want to make sure everybody understands what's going on, okay? And that is that when you said this is the case, that's good enough, okay? When you said this is the case, that's good enough, okay? So, all right. Let's see what happens next. We are going to look at the next example. The limit of absolute value of x over x does not exist. We want to see why. First, I'm going to quickly remind you of the following. I hope you remember the definition of an absolute value, which refers to distance from 0. This is x. If x is larger than or equal to 0, and it's negative x if x is less than 0. Therefore, if you want to evaluate this one, you are going to write, let me use a different color. This is x over x equals 1 if x is larger than 0. I'm not going to write equal because the denominator is x, and it will be minus x over x, or minus 1 if x is less than 0, and therefore we have the graph. Okay, class? Therefore we have the graph. Okay. So absolute value of x over x equals 1 if x is larger than 0, and -1 if x is less than 0. So if you were to look at the limit, I hope you realize, therefore, the limit of absolute value of x over x as x approaches 0 from the left it's -1. But the limit of absolute value of x over x as x approaches 0 from the right, +1. Okay. I hope everybody is okay with this. So the limit doesn't exist. There is a reason for that. So the purpose of this question, I wanted to make sure that we are reminded of what? We are reminded of a very simple thing, and that is the absolute value and the definition of the absolute value. Okay, everybody? As long as we know the definition of an absolute value, we are in good shape. Okay. Here's the next one. Now we are going to look at some algebraic techniques. Remember, the very first step is to simply plug in and observe. So what I'd like you to do, just plug in, everybody. Tell me what happens when you plug. That's all. Plug in. Anybody can see the answer when you plug in? If I plug in 2, I get 2 squared, which is 4 times 2. 8 plus 1 is 9. And this one is 3 times 2, 6 minus 2 is 4. So square root of 9 over 4, I just plugged in. And that's 3/2. So when you plug in, it results in a number and you're done. In part B, you plug in. So I hope everybody's okay with part A. You plug in and you're done. Okay? So can anybody tell me what happens when we plug in?
Do you get indeterminate form, like equals
Be more,
0?
yeah, indeterminate form of, go ahead, you were saying.
Well, that's all I know. I think it's
Okay.
just like 0/0.
Good, good. That's all I'm asking. Very good. You get 0/0, which is indeterminate form. Perfect. So if you plug in, you get 0/0. Now, what are we dealing with here? This is called a complex fraction. So in the case of a complex fraction, to change it to a simple fraction, we're going to multiply the top and the bottom by LCD. That would be the technique. So it's 0/0. We multiply by LCD, the least common denominator. As you can see in the numerator, we have two fractions. And for those, and the bottom doesn't have any fraction. So for those two fractions, the LCD is 4x. We are going to multiply by 4x over 4x. First, as far as the denominator is concerned, don't do anything, write it as a product. All you have to do, multiply 4x by the first one and by the second. So when you multiply the first one by 4x, the 4 and 4 cancel each other. So let me just, okay, so this one, if you multiply by 4x, 4 and 4 cancel each other, you get simply x. If you multiply this one, you get rid of the x and you get 4. And now, this is a very simple case. You see a common factor of x plus 4. They cancel each other. Okay, class? And now, practically you're done because you get the limit of 1/4x as x approaches -4. And if you replace this with -4, the denominator becomes -16. So -1/16 is our final answer. All right. In part C, a couple of things I want to mention. Number one, if you plug in, you get 0/0. Number two, anytime you have a rational expression, you want to ask yourself, can I simplify it? Remember that. Number three, x is approaching 5 and you don't want to mix it up with infinity. So if x is approaching infinity, you divide by highest degree term in the denominator. X is not approaching infinity. That is not the technique. The technique is factoring, okay? And here's the hint I'm going to give you. If you have a rational expression when you plug in gives you 0 over 0. It is the 0 in the denominator which is a problem. So most likely there is a factor that you can find easily because x is approaching 5. There should be a factor of x minus 5. If it was 7, would be the factor of x minus 7. If x was approaching negative 5, there should be a factor of positive 5. So you are going to factor the numerator, which is in the form of a squared minus b squared. Okay, everybody? Okay, difference of squares. And that becomes x minus 5, x plus 5 in any order. And the denominator, you just take a common factor of x. Common factor of x. X minus 5 is in common, and it drops. X minus 5 is in common, and it drops. So what happens next? Very simple. You plug in. When you plug in class, 5 and 5 becomes 10. The denominator is 5. And changes to 2. 10 over 5 equals 2. 10 over 5 equals. All right. We're going to look at more examples. Same thing happens here. If you plug in, you get 0 over 0. And I gave you a hint, class. I hope you use that hint. Normally, it is the 0 in the denominator that creates a problem. X is approaching 4. So we should have a factor of x minus 4. So you want to take the top and factor it. There is really not much you have to do. Just take out the x. LCD, GCF class, the first step in factoring, it's always GCF. GCF stands for anybody?
Greatest common factor.
Beautiful. So the top, you take out the x. The bottom one, you want two numbers. The product is C, which is negative 4, and the sum is B, which is negative 3. You already have an idea. Most likely you have x minus 4, and so you can factor it accordingly. As you can see, the common factor of x minus 4 drops, and you are left with x in the numerator, x plus 1 in the denominator. Now, remember, we are carrying the limit all the way to the end. You cannot drop the limit sign. It just moves on, and it keeps up until now that you replace it. So this becomes 4. The bottom 4 plus 1 is 5. And now we are done. Can anybody tell me what happens here if we plug in? Just plug it. Give me the number. Just plug in elementary algebra class. If you plug in, you get 0 over 0. Do you see that? Because 0 gives you 1, square root of 1 is 1, 1 minus 1 is 0, and the bottom is 0. So you get 0 over 0. Anybody remembers the technique involved? What did we do whenever we came up with a square root where the result was 0 over 0? Anyone remembers that? We've done that. The technique was to multiply by its conjugate. When we say conjugate, basically this negative change it to positive. So you're going to multiply the top and the bottom by its conjugate. So the result is that you're going to square this piece minus this piece and it comes out. So I'll write it for you. So you have the following: 1 plus h under the radical squared minus 1 squared. This comes out, this becomes minus 1. So that's the numerator. What about the denominator? Don't do anything. Write it as a product. So 1 and negative 1 cancel out. H and H, they cancel out. This is what you got. If you plug in 0 instead of H, it gives you square root of 1, which is 1, plus 1 is 2. So 1/2 is your final answer, everybody. 1/2 is your final answer. Okay. Let's look at this example. Can you see what happens if you plug in -4, class? When you plug in -4, you get what?
0 over 0.
Beautiful. We are going to multiply by the conjugate. That means -5 changes to +5. And when we multiply the top as well as the bottom. And again, at the bottom, you just write it as a product. You don't do anything to it because, class, x is approaching -4, so we should have a factor of x plus 4. And as you can see it, we do, and that is going to give us a problem. Take a look. X is approaching -4. We have a factor of x plus 4 in the denominator. That's a problem we are hoping to get rid of. So what happens next? That's what we want to look at. When you multiply the two, x squared plus 9, so you get x squared plus 9 because it comes out, minus 5 squared. So you get x squared plus 9 minus 25. And these two, they add up to -16. By the way, I want to make sure that everybody remembers not to mix up the following. This order of operations gives you this. This gives you positive 25. Don't mix them up, class. Now, I hope you realize we can factor the numerator into x plus 4x minus 4 because of a squared minus b squared equals a minus b times a plus b. So we can now drop the common factor of x plus 4. We are dropping the common factor of x plus 4, and now we are writing what is left. Now we can replace the x with -4. When we do that, -4 at the top, -4, and at the bottom, -4 squared gives you 16. Okay, now 16 plus 9 changes to 25, and square root of 25 is 5. So this will result in -8 over 5 plus 5, which is 10. And of course, in its lowest term, -4 over 5. It's very simple, class. I'm going to look at the next page also. I was going to leave it for the students to do it at home, but let's do that. The first question, okay. So the first question, everybody, when you plug in, what do you get? So plug in. In fact, just give me the numerator. When you plug in for the numerator, what do you get? Anyone? Just the numerator.
3.
Beautiful, because 6 minus 6, this goes to 0, you get 3. Okay, that means continue. Now you're going to do the same thing for the bottom. You get 6 squared, which is 36, minus 7 times 6, which is 42, plus 12. And I hope you realize it just worked out. You don't have to do anything. Add up the top to 3, and the bottom is, this is what? Minus 30 and 36 is 6, and it changes to 1/2. So plug in, it works out, we are done. And that's the key. Many times you just plug in and it works out, everybody. Now, we've seen this before. The next one is a complex fraction. A complex fraction you have to multiply by LCD. And as you can see, okay, the numerator has 1 and 2 fractions. The LCD is 3x. We are going to multiply by 3x. We write the denominator just as a product. If you multiply 3x by the first one by 1/3, the 3 goes away and you get x. And if you multiply it by the second one minus, x goes away and you get 3. And again, practically you're done. They cancel each other. You get 1/3x. The limit of 1/3x as x approaches 3. And now if you replace this with number 3, you get 1/9 as the final answer, everybody. 1/9 as your final answer.